Hello, my name is Trevor Heglund, and I'm going to be talking with you about my senior project. My senior project involved the compression molding of a carbon fiber composite wheel center. This wheel center will be used with the Formula Electric SAE car on campus. I performed this project with another student, another manufacturing engineering student, Alex DeCarli, who will be specializing in the fixturing for this project. My industry advisor was Ken Gamble of Quattro Composites. He graciously donated the aluminum and the carbon fiber that we're going to be using in order to make this process possible and make this project possible. So thanks to Ken. And our technical advisor is Dan Waldorf. So a little bit about the agenda. I'm going to be going over the problem statement. I'll talk a little bit about the background and what was done last quarter, building up to the progress that was made this year. I'll also go over the design for manufacturability. There were some DFM guidelines that were needed in order to make the mold a success. I'll go through my mold design selection criteria that I had, as well as the successful mold. I'll go through the mold production process, a little bit about testing. I'll go through a little bit about cost of what the mold will cost, and the next steps in this project. So my problem statement was I wanted to design and manufacture the tooling necessary to create a composite wheel center that would replace the existing wheel center used by the Formula SAE electric car. Now the Formula SAE electric car uses a three-piece rim set rather, all three pieces being aluminum. The wheel center currently is aluminum, and my goal was to remove the aluminum wheel center and replace it with the carbon fiber composite wheel center in order to reduce weight and give it a little aesthetic looks as well. So a little bit about what's been done so far. Throughout this project, the decision was made early on to have this process be done using compression molding, and in order to have compression molding be the process in which that this project occurs, we were going to need sheet molding compound. Now, carbon fiber sheet molding compound is a material it's chopped, discontinuous carbon fiber strands, usually about 50 millimeters in length. It's a material with isotropic properties, and after it's cured, it's actually got similar properties to aluminum. It's a little more brittle, but a lot more resistant to fatigue and wear over time. But it has about half the density as aluminum. So that's why we decided to use sheet molding compound. It's used a lot by Quattro Composites, and it actually functions really well in compression molding. So here's a rendering of the existing wheel center that the Formula SAE team is using. It's the aluminum wheel center. As you can tell, there's a lot of features that are used. There are a lot of features that are used in order to reduce weight. So you have holes that are drilled through the part. You have they use end mills to hog out some materials in some areas, give it a nice, interesting look, but also to reduce weight overall, but still remain that that structural integrity that they need in order to operate efficiently. So this is the rendering I did of the existing wheel center, and in order to make a part that could be used in a compression molding, we couldn't exactly just copy that design because there's a lot of features that would cause problems in the molding process. So the basic design constraint that we had was to keep the envelope of the part the same. What the Formula team needed is to have our part use the same dimensions and the same thicknesses as the existing wheel center, so that way it can interface with the rim walls that they currently have. That way they don't have to purchase any rim walls, but we can just do a part for part swap. So what we did is we designed the entire part to have the same envelope as the current model, and all we did is change the internal features a little bit. So instead of having so many features on the part, we reduced that number, because reducing the amount of features will reduce the complication of the mold design. Each time you have a new feature introduced, that's a feature that has to be represented on the mold, which is going to increase your machine time, it's going to increase the cost of machining, and it's going to increase the difficulty of molding that part, because the part's going to have extra features to hold on to after molding. Another important thing is any features we did incorporate in the part would have to include a draft angle. Usually 1 to 3 degrees is advised. I use 3 degrees for each internal feature within the mold, so every island that was in the mold exhibited a 3-degree draft angle in order to aid in the part removal after the cure time. Also, you want to eliminate the possibility of knit lines. So that is done by encouraging the proper flow of the material. And in order to have the proper flow of the material, you need to give it an area to flow through. Knit lines are created when material has to flow around a feature. And what they do is these two fronts that come together, they kind of knuckle together and make a weak spot in the part. So with having so many holes in your wheel center, you want those to be strong parts. You don't want them to be weak by any means. So designing a part that will allow the material to flow properly and reduce the amount of knit lines is crucial. Another thing is to account for the shrinkage within the part. These epoxy sheet molding compounds that we're going to be using don't have that much shrinkage in molding. Maybe a fraction of a percentage in shrinkage, just a couple thousandths of an inch. Also, we wanted to round any sharp edges. So sharp edges in a mold is good for machining because you don't have to use that many ball end mills, but it's bad for molding because it gives areas of material, it gives areas in the mold the material the opportunity to bind up. Also, it gives the opportunity for improper filling. So molded and rounded features are good. They work together well. And then also, we wanted to design the part with the ejection process in mind. We didn't want to design a part that would be trouble getting out of the mold, because how are we going to have a reproducible process that that can be done quickly and efficiently if you can't get the part out as easily? So we needed to design the part with ejection in mind. How many ejection pins we're going to use, how are we going to get it out, what's the main method of doing it. All those things were important to consider during the design. So here is the actual part that I ended up with. It has the same envelope, the same thicknesses, the same diameter as the existing wheel center, but as you can tell, there's no holes in it. So in the molding process, what that means is that each extruded feature that we're going to have within the mold is going to have a clearance between the plunger of the mold and the base of the mold, and that's going to allow the material to flow over these extruded islands and reduce the chances of having a knit line. Now, these charges that are going into the compression mold are going to be, basic shape. They're going to have the same volume as the final part. So they're going to go in already on top of these features, and the compression mold is basically just going to squish them down and around this. Instead of having to go around the part, it's just going to be squished down over it, which is going to actually improve the material properties over time. And then what's going to need to be done is secondary machining or cutting of some sort that will finish out the holes and locate them properly within the finished part. So now that I had my basic part designed after going through some DFM guidelines, I needed to design the proper mold. And I had 4 different design criterias, and I wanted to weigh them against each other to decide which one was the best for this process. As you can see, I had different categories. I went through repeatability, I went through manufacturability, safety, ease of the removal, how easy is this part going to come out, the cost options, which mold is going to cost more to machine depending on how many features it has or how many different moving parts it has. I looked at the secondary process needs, how much of the part that's coming out of the mold is going to need to have done to it afterwards. I also looked at how easy this mold is to handle and work with, and the overall complexity of the mold, and I gave it a certain ranking or weight to each one of these criteria or these categories, and then I went through and rated each design from 1 to 4, 1 being the best design, 4 being the worst, and I went through and weighted and rated all of these against each other. And what that yielded was a total score that had the weight and the rating multiplied by each other. And basically what you want is the lowest score possible. If you have a low rating and a high weight, that's gonna give you a high score, and that's not what you want in this case. So you want a low score. So the designs that actually came out on top were design 3 and 4. They actually had the same score at the end of the weighting. So that left it open to me in my interpretation of what I thought, which mold design I thought was best. And I went with the 4th design because it had a shelf that allows the ejector pin to sit in the same location every time. It's also easier to handle when you're thinking about moving this product from spot to spot. So that's what I went for, because I'm going to be the one that's handling this mold. So here's a drawing of the mold base. As you can tell, it has all the features down about 1 inch within the mold. This is to allow for the plunger to move in and have it be a true positive mold where all of the pressure is being exerted on the part. So having it down in that cavity is the way to do it. You can see the hidden lines for the ejector pin. There's going to be a shelf for the ejector pin to sit on, and there's also 4 little areas around the exterior of the mold that are basically open gaps that allow tools to be put under there after molding. So if a part gets caught in that that open section within the mold during the ejection, if it gets wedged in there, gets a little cockeyed and gets stuck, we can use screwdrivers or picks to get under there and pull the part up and help get it out easier. So those were some features that were added later on in the design in order to aid in part removal. Also, there's handles added, so that way taking the mold out and in of the press is much easier to grab onto, especially because it's going to be heated up rather hot. Here are the mold and plunger and ejector pin designs. So the plunger design is pretty basic. It uses the back side of the wheel as, it generates the feature of the back side of the wheel. And it has handles as well, so that way you can get your fingers in there to pull the molds apart, because this is all a hand-done process. There is no automation involved with the equipment here on campus. And then the ejector pin, which has a 3-degree draft angle around the top where it's going to be contacting the SMC material, and then that shelf along the bottom in order to sit in the mold properly. And then here's the completed mold design and how it looks when a part will be in it, and the injection sequence itself. So the plunger will come out, and then the ejector pin will eject the part out of the mold. So for the mold production, after I had these designs, what I did is I went into Creo and I developed the machining paths that were necessary in order to machine these molds in-house by myself. And what I did is I machined both the base and the plunger in a Haas VF2, and the plunger was finished on a lathe with a 4-jaw chuck, just to make sure it was completely circular and would drop easily into the mold base, because there's such a tight tolerance between the base and the plunger. The base hole was about 4 thousandths larger in diameter than the plunger, just to discourage flash from coming up in that open area. The ejector pin was also machined on a lathe. After all 3 parts were created or machined out, we had to sand them down and polish them by hand after machining, and that was a lot of work done by hand. In general, the total machining and polish time was about 22 hours. Now this is an estimate based upon what it would take an actual machine shop to do it, based upon the machine time that was running, the setup time, and the polishing. 22 hours is not what it took me to do this. I ran into a lot of hiccups along the way, a lot of redesigns, a lot of issues with the machine, which I had to stop and think about a lot, because I only had these 3 pieces of aluminum, and I didn't have more than one opportunity, so I had to take things and learn as I was going. So this 22 hours is based upon what it would take an actual machine shop to do that has experience and that makes a living in this type of production, and not actually the hours that I put into it. The testing was done just to see how the mold was. Right now we're waiting on the SMC material. It's on its way up to campus, so we still have not made a part with the SMC. Hopefully that will be done by the time you visit Cal Poly in the next few weeks, and I'll be able to report out on the process involved. But since I wanted to test the mold to see how well it worked, I went through and tested using a 2-part urethane resin casting material. So you mix it together much like an epoxy, and you pour it into the mold, and you allow it to set up. And it yielded a strong part that proved that the mold was effective and that it's working properly. The ejection pin functioned perfectly, held onto the part. Features filled out correctly. Everything was shown how the material is going to look after, and the actual features that it has. It actually showed areas where you might need more sanding within the mold as well. So that was good to do, to show and prove the validity that this mold does actually work and is ready for the SMC compression molding. After the testing, I went through and just kind of analyzed the cost of the mold itself. Basically, I applied a average mold shop cost. They charge about $150 per hour for an average mold shop to create molds that are sent to them and that are already designed. And with the 22 hours processing time times that flat rate, and including the aluminum stock price from the supplier, the total of this mold came out to be about $3,804. I have not done the cost analysis for the part because I have not received an accurate invoice for the SMC material yet. And once that happens, I can include the basic labor rates, the material cost, the mold cost, and everything into one into one equation and calculate out how much each part would be based upon the quantity. So if I'm making 4 of these parts, how much each would be. If I'm making 400 of these parts, how much these would be. And I'll have that done hopefully by the time you guys are here as well, after we have created some parts. So what the next steps are is to conduct the cost analysis of each part in order to determine how much these things are costing a company if they were to make them in-house. The mold components, I need to put them in the press once the material is received, so I can start generating the proper methodology for creating the part of a good quality and a reproducible quality that is what the formula team will desire. And then after that, Alex will be designing the fixturing for the machining processes that come after my molding process. So drilling the holes that are on the exterior of the part, drilling the bolt holes, and removing the material that was left behind from the molding process. So those are the things that we're looking forward to. I'm looking forward to finishing up what I need to finish in order to present out to you guys in the next few weeks, and you'll be able to see a part and see one in hand. So I want to thank you for your time, and I'm looking forward to meeting you. Thanks.